Okay, so the second part of part one is all about atomic mass, and so on your video on Canvas over the notes, I kind of go through all of this detail. So I'm not going to spend a lot of time on that right now. But what I do want to talk about is the calculation part down here. So, well, before I get into that, let me just point out, I want to reiterate that atomic number, mass number, and atomic mass, all three of those are completely different things. Okay, they are different terms, they have different definitions and different meanings. Okay, atomic number is your protons. Okay, that's how we identify the element or the atom. Mass number is your protons and neutrons added together. It's all the particles that have mass. So both atomic number and mass number are always whole numbers, whereas relative atomic mass, that one is going to be an average calculation. It's a weighted average, and so it's not ever going to be a whole number. It's always going to be something that has some decimal places because it's a calculation. It's not just a count of particles. So a lot of this I go through in the notes video, which you guys can watch if you haven't already. But I want to come down here and talk about how we calculate this. So there's a couple different ways the problems might be presented to you. They could show you a graph like this one, and you need to know how to read or interpret this graph to get the information. Okay, because to calculate relative atomic mass, it's a weighted average. And so what I always do is I always do the percent times the mass. I do that for each isotope. And the catch is the percentages, I have to change them to decimal form. So for example, when they say relative abundance right here, see how it has that percent sign? So relative abundance is the percentage. So if they use the term relative abundance or abundance, that is your percentage. That's the number for the percentage. Oh, let me see. I think somebody's trying to get in. Yep. Hey, Itzel, we just kind of started talking about our average atomic mass stuff. And so on this graph, the percentages are on the y-axis. So they're actually these numbers that are at the top of each of these little peaks, okay? And so I have this one, the first one is 2%. The second one is 24%. The third one is 22%. And the last one is 52%. Okay, so if I need to use these to calculate the average atomic mass, I need to change all of them to decimal form first. Okay, right now they're percentages. So I did talk about this in the note video, but to change something from a percent to a decimal form, I divide by 100. Okay, because that's what a percentage is. It's out of 100. And so in order to divide by 100, what that makes me do with my numbers, that makes me move the decimal 2 places to the left. So if I want to change all of these to decimal form, since all of these are whole number percentages, the decimal's at the end, and so I just move it 2 places to the left. And so then if I wanted to rewrite these for what they're actually going to look like when I put them in the problem, the first one is 0.02. The second one is 0.24. The third one is 0.22. And the last one is 0.52. Okay. It's important you remember that step because if you don't change those percents to decimal forms before you use them in the calculation, you're going to get the wrong answer. Okay. So then what you do is once you've converted your percents to decimal, you follow this pattern right here. You multiply each percent times the mass for that isotope. So for the first one, the one that I have here in green, the one that was 2%, and so now it's 0.02, that went with this line. And if I look, the x-axis is where they give me, they call it the mass to charge ratio. And typically that's going to be where you would read your mass, because a lot of times the charge is going to be 1. And so the ratio is just the same as the mass. Okay. So on this one, the mass is 204. So what I would do is for that one, I would do 0.02 times 204. Okay, that's for my first isotope. For my next isotope, If I look at this one, this is the one that was in blue. The decimal was 0.24 after we changed it from the percent. And if I look at the mass down here, it's 206. So I would multiply by 206. The same thing, the next one, I just kind of keep going until I've done each isotope. So this one, I'm going to have to do it 4 times because there's 4 isotopes. So the next one, the purple one, is the 22%. So it's 0.22 times, and the mass on this one is 207. And then my last one, this is the one with the highest percent. It's actually, I'm going to write it down here. It's 0.52 times, and the mass on this one is 208. So what I do is I do each one of these, okay? I multiply each one, so 0.02 times 204, 0.24 times 206, 0.22 times 207, 0.52 times 208, and then once I do that, I add all of them up, okay? And that would give me my answer. Okay, so this is how you do a weighted average calculation. For each of the things, which in this case we have isotopes, so we have 4 isotopes, and they gave us the abundance, the percentage of each one, and so we multiply that percent in decimal form times its mass, and then once we do that for each isotope, then we add them together, okay? And I believe I'm trying to remember from the notes video, I believe this one is 207 point, I want to say it's 22. I can't remember off the top of my head, but you can watch the notes video. It has the answer. I think it's 0.22. The one things, some things you want to keep in mind, okay? Even though this is a weighted average, it is still an average, okay? So even though if we look at our numbers, we had 204 and then 206, 207, 208, and we didn't just add them up and divide by 4. We didn't do a normal average, but we still did a weighted average. So my number, my answer should be somewhere between 204 and 208. So if I get a number that's lower than 204 or higher than 208, something is wrong somewhere in my calculation, okay? Because an average means that it's going to be between somewhere in the middle of my highest and lowest values. So even though it's not a normal average, it still is going to be somewhere in between those high and low values. So between 204 and 207 on the, 208 on this one. So 207.22, that makes sense logically because that's between 204 and 208. The other thing you want to keep in mind is that the percentages, okay, each of these percentages affects the overall average differently. The one that has the highest percentage, which happens to be the 208, that one has 52%. So that one is going to have a much greater impact on what the average is. That means the average is probably going to be closer to the side where like 207, 208 are than it is to 204, because 204 is only 2% right here. That barely affects it, if that makes sense. So then when we look at our answer and we see it's just a little bit above 207, that makes sense because over half of the sample, 52%, was 208. The other 48% was the other 3 isotopes all together, and 204 was the smallest, okay? So 206 and 207 were kind of close to each other. So when you're thinking about your answers, guys, think about the percentages, think about the masses, and check, like, does that answer make sense based on the numbers I was given, okay? They also might ask you something about most or least abundant. If they ask you about most and least abundant, I mentioned this in the note video, most abundant, that's going to be the one with the highest percentage. So which one is the most abundant on this graph? Which isotope mass, I guess I should say. So we got four of them here. Which one has the highest percentage? Which one has the highest peak on that graph?
52.
Yeah, so 52 is the highest peak. So if they ask me which isotope is most abundant, it's the one with the mass of 208. And if you read the problem up here, it tells you that these are all lead. They're Pb. So the most abundant, I would say that it's lead 208. That's the isotope that's the most abundant. The least abundant would be this one over here. It'd be lead 204 because it's the lowest percentage. Okay. Now, the other way you'll see these problems given to you is like your other practice ones on here. They may not give you that graph that you have to read and figure out what where the charges, not the charges, the masses and the percent abundances are. They may give it to you just in the problem, like on your practice ones that you're going to do. So, or it might be in a table. We're going to take a look at some practice ones where it's going to be given to you in a table. And so, for example, on this first one, or on letter A here, it says rhenium has 2 naturally occurring isotopes with the following natural abundances. So here are the abundances. Those are the percentages. And then they don't give us the masses written out, but in the symbol, remember this top left number, that's the mass number. So if they don't write out a separate mass, I use that mass number from the symbol. So for the first one, I have 185 and then my percent's 37.40. For the second one, my mass is 187 and my percentage is 62.60. So which of these two, looking at these, which one do you think the average is going to be closer to? The rhenium 185 or the rhenium 187? Because this is not, it's not like they're equal, right? It's not like we're just adding them up and dividing by 2 like a normal average. So it's not like we're going to add 185 and 187 divided by 2 and we're going to get 186. That's not what's going to happen. We're going to have to use those percentages. So look at the percentages. Which percentage is higher?
Rhenium 187.
Rhenium 187. So that means when you get your average, it should be closer to 187 than it is to 185. Because this is 62, almost 63%. This one's only about 37.5%. Okay. So think about that when you're doing these problems. The higher percentage, your average should be closer to that one. Okay. So when I get the answer, it should be closer to 187 than it is to 185. So it should be probably 186 point something. All right. The next one, same process. The only difference is it's got 7 isotopes. So you have to do that process for all 7 of these and then add them up. And then the last one, this one has, okay, so this one you're kind of going backwards on this last one. So on this last one, it tells you that the element europium has 2 naturally occurring isotopes. Here are their masses, okay, europium 151 and europium 153. And look, they give us the relative atomic mass. So on this one, you're working backwards. They want you to calculate the percent abundance. So the way that you would set this up, okay, is it's kind of like algebra. So I know that if I do, percent times mass plus percent times mass, that's going to equal that relative atomic mass, right? That's what we just said. So on this problem, they have given me the 2 masses and they have given me the relative atomic mass. They did not give me the abundances. They want me to solve for both of these percentages. So what you have to do in a situation like this, when they ask you for the percent, is we're going to pretend, because it's a percent, right? So it's out of 100. And so remember, we have to convert them to decimal form. So when we convert them to decimal form, instead of being out of 100, it's now out of 1. So what I'm going to do is I'm going to pretend one of the percentages is X. It doesn't matter. I don't care which one you pick. You can pick the first one or the second one. But what I would do is I would say, okay, well, X times the mass times 151. We'll go ahead and plug that one in. X times 151 plus, now this one, I don't want to call it X because it's a different percent. But I know that they're out of 100. I know that if I add the decimals together, I'm going to get 1. So what I'm going to do is I'm going to call this one 1 minus X. Because I know that when I add those percentages together, they're going to add up to 100. Or if I add their decimal forms, they're going to add to equal a total of 1. And so what happens on this is if you're given a problem like this with 2 isotopes, you can solve for it by making one of them be X and the other one be 1 minus X. And then just remember, I still have to multiply that by 153, okay? And then that equals the average. It equals the 151.96. So then from here, it's algebra, basically. So I have if I'm going to rewrite this to kind of simplify it. So I have 151x, right? Because I'm multiplying that. Plus, now here I have 153 times 1 minus x. So remember, this has to distribute to both of those. So that becomes 153 minus 153x. Everybody okay with that, what I just distributed on that one? So 153 times 1, and then 153 times the minus x. And then that still equals our total over here, the 151.96. Now from here, I'm going to combine like terms, right? So if I look, I have a 151x and I have a minus 153x. So if I combine those together, what's that going to be when I simplify it? Yep. Michelle just said it. I don't know if y'all can hear because I think she's on mute. So the 153 stays the same, but if I combine those x's, this is just like we're in math class, 151x and negative 153x, that's going to be negative 2x. So it's minus 2x equals 151.96. Okay. Now it's looking a little easier because now I can subtract 153 to the other side. And then after I do that, then I divide both sides by negative 2 to get the x by itself. Now, once I get the answer for x, okay, that tells me the answer for the 151 mass. So this is where you got to be careful. Remember, x is where we made that the percent for 151. To get the answer for 153, I have to do 1 minus x. Okay, and then after I get, remember, x is in decimal form. So they want the percent abundance. So that means I have to multiply it by 100. So what we would do if we kind of keep working this out, okay, I get negative 2x equals, that's going to be negative, what's that going to be? 151.96 minus 153, negative something, negative 1 point something. 151.96 minus 153, so negative 1.04. And then divide both sides by negative 2 because I want to get x by itself. And when I do that, I get x equals 0.52. Okay. So that means that 1 minus x equals 0.48. Because if I do 1 minus 0.52, if I plug that in for x, that gives me 0.48. So these are my two numbers. But remember, I got to make them percentages because they asked me for the percent, not the decimal form. So the last thing would be both of these would have to be multiplied by 100. And so I end up getting 52% and 48%. Now, how do I know which isotope they go with? You go back up and look at your problem. Okay, we assigned x. X is the 52%. We assigned that one to the isotope that has the mass of 151. The other one, the 1 minus x, is with the mass of 153. So what I would say is that this sample, it is 52% europium 151, and it's 48% europium 153. So like this is the hardest type of problem that you would have to do, is where they give you the average and the individual masses and they ask you to find the percentages, but they'll only ever do it for ones that have two isotopes, because that's the only, mathematically you can only do it with two isotopes, because we can say one's x and the other's 1 minus x. If you have more than two isotopes, there's no way to do this mathematically, at least simplistically. But a lot of times you're going to be asked to do the other part. So you have these two practice ones, 1A and B, that you can practice doing the average calculation. But what I'm going to do now, I'm going to switch over. See how much time we have left. We still got about 10 minutes. Yeah. So I'm going to switch over because I want us to look at a couple of other practice type questions over what we did on Tuesday and what we're doing today. So let's see how many people did the video notes. Can anybody answer number 1? So there is a machine that's used to detect the isotopes that's talked about in the notes. You guys know which one it is?
A?
It is the mass spectrometer, and so the technique is called mass spectrometry. Okay. Titration, that's what we just talked about with solutions. That has to do with the solution concentration. Recrystallization, that's just where you're having something that was a solid and maybe it's now a liquid or solution, it's turning back into a solid. That's recrystallization. And then infrared spectroscopy is another technique that we will talk about in another topic. So we haven't gotten to that one yet. So that's a basic, like, just a definition type of question. What about, let's look at number 2. Number 2, they've given us a symbol for an isotope, for an element, and they want to know what's represented by the letter A. So this is another vocab type question. So which one is it? Which one is not A? Let's see if we can eliminate some answers if we don't know the exact answer.
The proton.
It's not protons, because protons, that's Z. Z is the atomic number. That's the proton. So it's not D. And then in our symbol, do we ever write the number of electrons or neutrons?
No.
No, because remember, those are the ones that we have to calculate. So neutrons, we always have to calculate. Electrons, it might be the same as the atomic number, but sometimes we have to calculate them as well. So if you know that those 3 are what they are, then by process of elimination, you should be able to figure out it's C. And if you didn't remember, nucleons, that's one of those new words that we had in topic 2.1 on Tuesday. Nucleons is the term for the protons and neutrons. It's the term for all the particles in the nucleus collectively. And so that includes protons and neutrons, which, remember, that's also equal to the mass number. So the mass number is A, which is protons and neutrons, and those are also called the nucleons. And so that's really, you had to know that term nucleon and what that meant and how it related to the particles and what we write in our symbols. Okay. Okay, this next one's related to what we just did today. So it says bromine consists of 2 stable isotopes which exist in an approximately a 1-to-1 ratio. The relative atomic mass of bromine is 79.9. Which are the stable isotopes? Okay, so there's a couple things that we need to understand here. What does it mean if something is a 1-to-1 ratio? What does that mean, like, mathematically or number-wise? You guys know what it means? Or could you explain it to me? So think about when we do our balancing equations and we say something's a 1-to-1 ratio. What does that mean? They're the same amount, right? So when they have a 1-to-1 ratio, that means they both have like a 1 coefficient. So they're using the same amount in a chemical reaction. So if something is a 1-to-1 ratio, that means they're equal amounts. And so this one, notice it says approximately. So they're telling us it's like almost equal. It's almost a 1-to-1 equal ratio. So if they're 1-to-1, that means that they're each about 50%, right? Because that's half, right? Half of 100%. And if they're 1-to-1. So what they're telling us is that if they're almost equal, it should be a 50-50 split. And so if we average, we really would do it like a normal average, right? We would add them up and divide by 2 if they're all split 50-50. So the way that you would work this out is you look at the masses. So A has 79 and 81, B has 80 and 81, C has 78 and 80, D has 79 and 80. So if I do the average, if we start, it doesn't really matter which one we start with, but if we start with like D, 79 and 80, if I add 79 and 80 and divide by 2, what am I going to get? What do you guys think? So if I add them up and divide by 2, it's going to be right smack in the middle, right? So what's halfway between 79 and 80? 79.5, right? Because it's a half. So then if I look at C between 78 and 80, so if I add those and divide by 2, Or if I look at what's right halfway between 78 and 80, what's right in the middle of 78 and 80? That one, yeah, that one would just be 79 even, because that's the average. What about B, 80 and 81? What's halfway between them? So that's another one where it'll be a decimal, 80.5. Okay. And then what about A, 79 and 81? This is kind of like C. This one will be a whole number because it's got a whole number in between them. 79 and 81, which one would be what would be the average there? Be 80, right? Because it's right in the middle. So of these, which is closest to 79.9 of the 4 we just did? Michelle says A. She is correct, 80. Out of all the options we have, 80 is the closest to 79.9. It's only 0.1 off. Another thing you could look at, remember we talked about that these averages, they're still averages. So they still have to be between the two numbers. And so if I look, B like should have been eliminated. We really shouldn't have even checked B. Because if the numbers on B are 80 and 81, but my average is 79, that's less than 80. So that logically, that doesn't make sense for that one to be the correct one. I think I'm frozen because I've written stuff on the iPad, but it's not showing y'all. Why isn't it catching up? So on number 3, that one would, again, that one would be A, because when I do the average, since they are 50-50, that is where I can just add and divide by 2. So the average would be halfway in between my 2 answers. And so then doing that for all 4 of them, the closest one to the answer in the problem, the 79.9, is the 80 on the letter A. What is going on? Let me turn it off and reconnect. Maybe that'll help. Okay, so now y'all can see what I kind of wrote in red. So A is the answer, because again, the 79.9 is closest to the 80. Okay. Let's look at, I was gonna look at, okay, so number 7. This is also another one that has relative atomic mass. So it says a sample of zinc has the following composition. So there's 3 isotopes. Here are their masses, 64, is that 66 and 68. And here are their percentages. And then it wants us to do the relative atomic mass. Now, I will tell you, I think this is an old question because this one would probably not be on our test because we don't have a calculator, right? And so since there's 3 isotopes, they're not all split, equally. This would be a pretty difficult one to do without a calculator. So more than likely, instead of having answer choices like what they have here, the answer choices might look more like the setup. So they might expect you to know that it's like 64 times 0.55 plus 66 times 0.40 plus 68 times 0.05. So that would probably be more like what the answer choices would look like on our test now, because they know you don't have a calculator, so they're not going to expect you to do this. However, we could, kind of guesstimate, okay, based on the numbers. So if you look, most of the mass is 64 and 66, right? Like 95% of it's in there. So I would say since it's mostly 64, but somewhat 66, I don't think it would be D because that's too far above 66. And it wouldn't be 64.5 because the 66 would be influencing it too much. And it probably wouldn't be right in between them either, because that's right halfway in between, and we have that 5% that's 68. So it's probably either B or C. I'm leaning more towards C. I'd have to do the calculation to actually figure it out. But they would probably be more likely to give you an answer choice that you'd have to look at what the setup is, like this one. Okay. And then here's another one that it says, consider the relative abundance of the isotopes of element X. What's the relative atomic mass? And so on this one, they're not asking us for an exact answer. If you look at the choices, what you would do on this one is kind of what I was talking about earlier, use these abundances. So look, this one's 80%. So if that one's 80%, it's probably going to be really close to 24, right? But there is these other percentages that are affecting it a little bit, okay? And so this is where you're kind of using your logic, okay? It's definitely not going to be exactly 24 or 25 because we have other percents affecting it. We have that 26, so that's going to bring it up a little bit. But do you think it's going to be between 24 and 25 or between 25 and 26 based on the percentages they gave us? What do you guys think? So which one is the most abundant one? The 24, 25, or 26? Which is most abundant?
24.
24, right? It's got 80%. And in the notes, I told you guys the most abundant one, that means the average is probably going to be closest to that one. So it won't be exactly 24, but it'll be pretty close to it, which means that the only answer that makes sense is C. It'll be somewhere between 24 and 25. It'll be pretty close to 24, but it won't be exactly 24 because these other two, the 25 and 26, are affecting it. It doesn't make sense that it would be between 25 and 26 because the 26 is only 10%. Okay, so that's going to make it a little higher, but it's not going to be high enough that it would be more than 25. Okay, and so that's kind of how you have to think about those types of questions. All right, I am going to stop sharing because it's time for us to switch over. So you guys have your other practice ones that you're going to be working on.